Good day, viewers. This is 300 Plus Academy, where all we do is exams tutoring, ensuring that you ace your next and every exam. It's about time for the beautiful subject physics. This time around, we'll be looking at bifilar suspension, or you simply say bifilar simple harmonic motion. This time around, we are looking at periodic oscillatory motion about the equilibrium position. So for this particular question on bifilar suspension, it's a mechanics. What are the things we are going to be provided with? We are looking at pre-retouch stand with clamps. You can see that on your screen. G clamp, spiral spring, 100-gram mass labeled M, 2 pieces of thread with loops, stopwatch, an optical pin, and the sellotape. So looking at all these experiments, we can actually predict what our question will look like. 3 retouch stand. You're going to have a retouch stand this way and another retouch stand this way. From this retouch stand, you're going to have a thread. You're going to have a thread with a loop. When we say thread with loop, it means you're having your thread this way and then with a loop this way. So this loop of the thread is going to hold a meter rule in between the 2 retouch stand, and then we're going to have a third retouch stand here. Now this retouch stand is good with a G clamp, is going to hold another meter rule, and this particular meter rule here is what will be used to get the vertical height of the thread from the position of the clamp here to where we have the first meter rule here. So in this case, once this first meter rule is being held by this inextensible thread here, we are sort of going to set this into a very small angular rotation. We hold it at the midpoint. You can see in the diagram on your screen. We hold it about the midpoint, set it into oscillation, and then what we're going to have is a situation whereby this meter rule being held here is going to move forward and backward, it's going to produce what we call a turning effect, such that when this side here moves this way, this side is going to move this way, and like that, to and fro, to and fro, to and fro. That is what we mean by bifilar suspension. So what should our question look like? As you can see on your screen, it says attach the mass M 100-gram firmly to the rule AB at the midpoint, that's at the center of gravity, using a sellotape. That you're going to do, you're going to attach here. After that, suspend the meter rule by 2 parallel threads of length 80 centimeter. It means the length from here to here should be 80 centimeter. From here to here should be 80 centimeter. It should not be bending or slanting. It should be balanced horizontally. Each at the 10 centimeter and 90 centimeter marks. You see, 10 centimeter marks, 90 centimeter marks. Then you set, the next instruction says, ensuring that the graduated face of the meter rule is facing upwards. The graduated part of the meter rule is facing upwards and not downwards. This is the mass, 100-gram, attached to the center of gravity at the midpoint. It should be facing upward in this suspension here. It should be facing upward and not downward. After that, it says also the distance between this thread, the distance between the thread is represented as D and should be kept constant through this experiment. This is going to be 80 centimeter, as you can see. D here, from here, this is 10, this is 90. 90 take away 10, now it's going to give you 80 centimeter. That is our D. Invariably, it means that our D is 80 centimeter, or converting to meter, that's 0.8 meter. That will come handy as we proceed. Okay. Instruction 3 says set the rule AB into small angular oscillation. So it means at this point at the center, we're going to set it into oscillation, and then this will begin to and fro movement, to and fro movement, to and fro movement, to and fro movement. Okay, it says we should determine the time t for 10 complete oscillation. Note the length for the first experiment, for the first reading, is the height of the thread to the meter rule is 80 centimeters. So for the first one, this is 80.00. We can keep that to 2 decimal places. When we perform the experiment, when the length is 80 and we set this into vibration, the timing at that point from what we have here is about the time for 10 complete oscillation, for 10 to and fro oscillation was 18.50. So if it will take 18.50 seconds for 10 oscillation, then what is period? Period is the time taken to perform just one cycle or one oscillation. That's one to and fro movement. So it simply means 18.50 seconds to move to and fro 10 times. So if we are looking at the timing to just move once, to and fro, that will be 18.50 divided by 10. This will be 1.85. 1.850. I could make this to 3 decimal place. Okay. And then the square of the period, we were told to express that. You can see in the question, the square of the period, 1.85 square, is going to give us 3.423. Okay. We can also be told in rare cases to express the logarithm of the period. Now that means the log of 1.85, that's going to give us 0.267. And we can, in rare cases, also be told to look for the log of the height of the inextensible thread here. The log of h here is log 80 is going to be 1.903. Okay, we've been able to deal, with the length of the whole system when the length of the thread is about 80 centimeter. Looking at the instruction, it says keep and record the value of d in meters. We've done that. D, that's the distance, the distance between the thread here and the thread here is 80 centimeter. Converting that to meter, that's about 0.8 meters. Okay, next instruction says repeat the procedure for other values of h equals 70 centimeter, 60 centimeter, 50 centimeter, and 40 centimeter. That means we have to reduce the length of this thread to 70, then 60, then 50, then 40. We've dealt with the length of the thread when it was 80. This is the time taken for 10 complete oscillation. This is the period for one oscillation. That means the total time divided by 10. And this is the square of the period. This is the log of the period. And this is the log of h, the height of the length of the thread. Okay, at 70 centimeter, when the length of the thread here is reduced to 70, the time taken reduced from 18.50 to 17. And when the length of the thread reduced to 60, the timing for oscillation, for 10 complete oscillation, even reduced. Recall that normally in physics, the period of oscillation is more of directly proportional to the square root of the length. So this is more like a direct proportion. The more the length, the more the time it will take, and consequently, the more the period. You can see when the length is 80, the period of oscillation, the period for one complete oscillation is 1.85 seconds. But when the length of the thread here is 40, the period decreased correspondingly to about 1.2 from 1.8. So that is it. The more the length of the thread, just like in a swinging pendulum, but this case, this is a bifilar, just like in a swinging pendulum, the more the length, the more the period it will take. That's the more the time it will take to complete one oscillation, as against when the length is shorter, then it's going to take a lesser time. So having said that, for all of this h, this is the time taken, and then to get the period, you divide by the number of oscillation, that's divided by 10, you get this figure. You look for the square of the period, you get this. You can't be told to express for the log of t. You have to do that, the logarithm of 1.85, the logarithm of 1.7, the logarithm of 1.5, and like that. Then log of the length of the thread itself is another scenario. You look for that logarithm, and that ends that. And then the next thing in the question says, plot a graph of t square on the vertical axis and h on the horizontal axis. So it means that for this particular experiment, we are plotting t square on the vertical axis and we are plotting h on the horizontal axis. This is our x-axis. This is going to be our y-axis. That's what this is. But in reality, as you can see in the question, you can also have a case where you're told to plot a graph of log t against log h. You can have a case of log t versus log h. It is very possible you may want to try that out on your own. A graph of log t as against log h. This will be your vertical, this will be your horizontal. You may try that out, but I will be trying the graph of t square as against the length of the inextensible thread here. So the next thing is to plot a graph of t square as against the length of the thread here. So the very first thing we want to write is, we want to write a title, a graph of t square in second square against h in centimeters. We've written the title, and then the next thing for us to quickly do is to take, our vertical axis, get it down, no broken lines. You want to make everything sharp as much as you can. Okay, I've been able to get my vertical, that's my t square axis, t square in seconds square. I've been able to get that down. And then this side is going to be the horizontal axis. So I want to ensure that everything is just perfect. This is the point where a lot of students miss out on valuable marks. Okay, this axis here, that's going to be my h axis. I am plotting t square as against h centimeter. Now for practice, you can try out, like I've said, log t as against log h. So the next thing, we already have the readings before now. Okay, let this be our zero origin. The next thing for us to do is to plot t as against h. But before that, let's try to look at our scale. From the reading, we have 40 to 80. Now this is going to be easy. If we say 20, okay, 10, 20, 30, 40, 50, 60, 70, 80. Okay, this just goes. This is more like, this just goes. This is more like 2 centimeter to represent 10. This is 10.00. This will be 20.00. This will be 30.00. This will be 40.00. This will be 50.00. This will be 60.00. This will be 70.00, and this will be 80.00. Okay, that just about does that for our h. Now, talking about our t square, you can see that we're looking at the highest being 3.423 and the lowest here being about 1.464. We're looking at, okay, 1, 2, 3, 4. That just does it. You want to ensure that your graph covers at least more than 60% of your workspace. Okay, this can be 1.000. This can be 2.000. This can be 3.000, and this here can be 4.000 for our t square, because our t square in this case, the max here is about 3.5 and the lowest here is about 1.424 for our t square. Another thing you want to ensure is writing down your scale based on what we are looking at here. For the t square axis, our scale here is looking, okay, from here to here is 2 centimeter, and from here to here is about 2 centimeter. That's about 4 centimeter to represent 1 unit. 4 centimeter to represent 1.000 seconds square. Yes. 4 centimeter, yes, that's about 4 centimeter to represent 1 unit. So that's 1.00 square. And then for our h, that's 2, from here to here is 2 centimeter. 2 centimeter to represent for h in centimeter. That's 2 centimeter to represent 10.00 centimeters. Okay, that is what our scale is. You know, everything is looking all good for now. So moving on, the next thing is to pitch our points. We have 3.423 and 80 and 3.423. Now this is going to be 3. This will be 3.1, 0.2, 0.3, 0.4, 0.5. So we're looking at 3.423. Here is about 3.1, 0.2, 0.3, 0.42, somewhere around here. This is somewhere around here, and you're going to have to pitch that as against the 80 mark. You have to pitch that as against the 80 mark. So you're looking at something around here, okay? That is looking something like this. That is looking something like this, okay? And then to the next one, that's 2.89 and 70, 2.89. This is 2.5, 2.6, 2.7, 2.5, 2.6, 2.7, 2.8, 2.89 somewhere around here. If I'm not mistaken, yes, it's somewhere around there, because this is 2.8. This is going to be roughly 2.89, okay, and 70. You want to trace that out. It's looking something like around here. So that is done, okay. The next thing is 2.403. The next thing is 2.403 and 60. 2.403, 2.1, 2.2, 2.3, 2.4, something around here. And you want to pitch that as against 60. If you trace that, that is looking somewhere here. Okay. That done. And the next thing is 1.852 and 50. 1.852. This is 1.5, 1.6, 1.7, 1.8. 1.85 is somewhere around here. Okay. You want to trace that to where you have your 50. Okay. So that's something around here. Okay. That done. And then the next one, which is the last one, 1.464 and 40. This is 1.5. So this is 1.46, something around here, and 40. Okay, this happens to be that point. Okay, so here we have our point already. So the next thing is to determine the slope x of the graph. So if we can get like about 3 points together would be cool. Okay, 1, 2. Okay, we're able to get roughly 3, just manipulation to make it 4. So I haven't picked our points this way. The next thing is for us to draw a straight line that at least touches on some of the points. Okay, we've been able to do that. Okay, been able to draw a straight line. We picked 1, 2, 3 points conveniently. Okay, how do we look for our slope? Is the change in y divided by change in x. Okay, so this here is going to represent my change in t square in second square, and this here I could just stop this here at the 1.00 mark. Okay, this here is going to represent my change in h in centimeters, so that my slope looks something like this. If I trace this, you trace with your ruler. If I trace this, this is 1. And here, where I am stopping here, I could trace where I am stopping here. I could trace things up. And get the job done. I'm going to draw my extrapolated line, so that I sort of indicate. Okay, I've been able to do that for the vertical axis. This is 1, and this is 3.1, 3.2, 3.3, 3.4, 3.40. Now here, this here is my, if I trace this, this is 80, and when I come here, this is 30, 31, 32, 33. This is looking 34. This is looking 34. If I trace that, this is looking 34. Yes, 34.00. So I know that when I'm talking about my slope here, it is going to be 3.40 minus 1.00 divided by, okay, I could calculate my slope here. My slope is going to be change in t square per second square divided by, so that your work is not going to be rough. You can calculate your slope outside of your graph. Change in t square in second square divided by change in h. That's in centimeter, and what that means here is 3.400 minus 1.000 divided by, you're looking at 80 minus 34, 80 minus 34, 4. So in that regard, our slope is going to be 3 points, is going to be 2.4, 2.4 divided by 80 minus 34, that is about 46. So if we compute this, we are going to get 0.052. Of course, not forgetting the unit seconds square per centimeter. This is what our slope is. And with this, we can now go back and work with what we have. Look at it very well. Take your time and you'll be able to get things done. Next question says, evaluate K equals to S over Q. Evaluate K equals to S over Q. Given that from the question, you can see that our Q is 2 over 25d squared, 25d squared. Recall that between the inextensible thread, this is our D here, and when we calculated our D, that's 80 centimeter, that's about 0.8 meters if we convert. So that is what our D will be. So we're told to evaluate K equals to, S over Q. Firstly, this will mean S divided by Q is 2 over 25d square, and this will be X times 25d square. This will move up, divided by 2, so that my K is actually this. So what is my slope from the graph is 0.052. 0.052 second square per centimeter. So I'm going to take note of the unit I am having here. I already have second square per centimeter, okay? And then times 25, and then my D is 0.8 times 0.8 square. Now 0.8 square, that will mean meter squared, all divided by 2. We already know that this will be the unit of our answer. Computing from our calculator, that will give us 0.408 second square per centimeter meter square. That is what our K is. When we are told to evaluate, we must put the units. So moving on to the next question, the question says, state 2 precautions taken to ensure accurate results. You can see that on your screen. I ensured that the support of the bifilar pendulum is rigid. I ensured there was no error due to parallax when taking my reading from the stopwatch. I had repeated readings. Of course, that's why we have 1 to 5 repeated readings, so that we get accurate results. That is already shown in the table. I ensured smooth and regular oscillation in a horizontal plane over small angular oscillation. I ensure the meter rule is not touching the table and the retort stand. I also avoid zero error in the reading of the stop watch. I take that into consideration when reading my time. So that talks about the precaution. You can see that. The next question says we should define the term couple as it relates to rotational oscillatory system. You can see that on your screen. It is a pair of forces of equal magnitude acting in opposite direction along parallel lines of action, but not along the same line. Okay, it's just like if this were to be a steering wheel. Of course, if you are, holding this side and then holding this side, one force is towards this side, another force is towards this side. You can see they are parallel force. When you talk about couple, you're talking about forces that produces turning effect. Is a pair of forces of equal magnitude acting in opposite direction along parallel lines. So that takes care of that. The next question says we should define simple harmonic motion. Simple harmonic motion is the motion of an object whose acceleration is proportional to its displacement from the equilibrium position and always directed towards that equilibrium position. In this experiment, this bifilar, when this moves this way and then comes back, then this goes and when this goes this way, this is coming this way. When this comes this way, this is going this way. This is an example of simple harmonic motion, in that the body will always come back. No matter how you displace it, you always come back to the equilibrium position. You can see the answer on your screen talking about simple harmonic motion. And then the last but not the least is we should give two practical applications of a couple in everyday life. Anything that produces turning effect when we apply two parallel force is an example. A tap is an example. For you to turn on a tap, if this were to be a tap, when you apply your force this way, there is another force going this way. Once you have parallel force, that is a couple. Opening and closing tabs, turning a steering wheel, riding or pedaling of a bicycle, turning a spanner, motion of a spinning spindle. These are all examples of couple in everyday life. And with that, we've come to the end of this experiment on physics practical WAEC 2025. Take note to plot your graph on the log of the period as against the log of the length of the thread H. And with that, we've come to the end of this lecture. From myself and the entire team, it's bye for now.